In the meantime, we've got Johan here that he's going to discuss where Stage 0 belongs on the landscape and show some restoration and examples. Johan is a watershed restoration specialist for the U.S. Forest Service and has been for 25 years. He's a lead hydrologist, specializing in collaborative restoration and water resource management. His focus is on large-scale meadow restoration, in-stream wood. Well, you can read it right there. I hate reading from slides here. So stream protection during forest management, and most recently, valley bottom Stage 0 restoration. He's also a member of the RATs, which are leading experts to consult with throughout the Pacific Northwest. So Johan, let me make you the presenter, and you, if you've got a screen up there, we can share your screen. So welcome, thank you.
Thanks, Jane.
There it is.
Okay.
That's perfect.
Great. Okay, let me minimize something here. Yeah, I think I'm there. All right, well, the first three presentations were excellent. Really appreciated all the information. I think mine's going to dovetail pretty well. Good morning, everyone. So Brian gave an excellent overview of the research and academic underpinnings of Stage 0. I'm going to repeat some of that. But to that overview, I'd like to add some thoughts about Stage 0 from the practitioner perspective, and how a group of us in the Forest Service have independently kind of come to this Stage 0 idea, and then have kind of come together with the academic community and talked a lot about it and worked together on it. Okay, so I want to just show you a little bit about disturbance history. I think Brian did an excellent job of describing that, and so some of mine will be a repeat. I want to show some of the restoration that we at the Forest Service have done over time and kind of evaluate that in light of the stream evolution model that Brian showed you, and then talk about how we as practitioners kind of move towards just kind of this evolution to Stage 0 restoration. And then I want to end with some examples across several ecoregions of Oregon. I have 5 projects that I want to show. They vary in space and time, and it just is going to kind of illustrate the fact that the principles that we're thinking about here in these depositional environments really apply across many ecoregions, climates, geologies, so forth. Okay, so first of all, this is a diagram that Brian also shared with you. When I was first starting out in the Forest Service, and we were doing watershed analysis, this was Montgomery Buffington's source, transport, and deposition. That was a pretty important concept to several of us as we were looking at our watersheds in kind of a different way. And essentially, Tim talked about the fact that the landscape processes affect habitat conditions, and habitat conditions affect biota. And that's exactly what I learned early on in my career, and that's that the materials that form kind of the basis, the building blocks of habitat, those materials like water, wood, substrate, fine sediments, organics, nutrients, all these building blocks, they start in these steeper source channels in our watersheds. They move through these transport regions, and oftentimes they hold up for short periods of time, and then they pulse down into the watershed. And they end up in these response reaches here, oftentimes at the bottom of our watersheds. And it's really these, as Brian talked about so well, these response reaches, these depositional valleys, are just something that we learned a lot about in our early years and thought about. And essentially, I learned 2 main things about these depositional reaches. Number one, They really were historically the powerhouse producers of fish and wildlife in our watersheds. And secondly, the fact that they are the most sensitive to disturbance. And in most cases in our watersheds, they were the first to be disturbed and to be affected. And these are areas that are flatter, they're wide open, alluvial valley bottoms, there's good soils there for farming, a lot of road building. So just your settlement, like Brian showed, really focuses on these response reaches. And then as he talked about, the upshot of all that disturbance and change is to gather up those waters in those wide open valleys and turn them more into transport channels than what they were historically. So instead of those building blocks, those materials coming out of our source through our transport, spreading and dropping, they're being pushed out of the system. Just one more note about this diagram. Oftentimes it's not as kind of simple and neat as the way Miller has it portrayed here. Oftentimes you see these response reaches, these depositional valley types, kind of intersperse along the way. So Paul Powers has kind of divided this up a little bit and shown sometimes you have these depositional valley types, and then they're kind of punctuated with these transport reaches. One really good example is in some of our more unstable watersheds where tributary fans come in, they form alluvial fans that pinch the valley. So you have a whole series of these alluvial fans, and you see this expansion and contraction as you go downstream. So just to keep that in mind, because I know Idaho has a lot of that. Okay, so stepping back, and this is really going to be kind of a cartoon version of what Brian so eloquently talked about, and also Tim and George. But essentially, when the pioneers first came to these depositional valley bottoms, what did they see? Well, and I'm a west side guy. I'm a kind of a wet side guy of Oregon, and so you're going to see a lot of conifer examples and a little more wet, but obviously they came here and they found a mess in a lot of these areas. Lots of vegetation diversity, elevational diversity, multiple flow paths, both standing and down wood, high water table, beaver dams, frequent floodplain wetting, and this idea of maximum patch complexity, which comes out of the terrestrial ecology literature. And the way I like to describe this is if you were a drone kind of hovering over one of these historic depositional environments, you would just see kind of a patchwork of different sizes of wood and vegetation and substrate, different water velocities, a lot of different complexities based on the materials that have dropped and spread in this particular valley. Maximum patch complexity. In 2013, Roney and Beachy came out with their book, Stream and Watershed Restoration, a Guide to Restoring Riverine Processes and Habitats. And one of the things they did really well in this book is they characterize processes at both the reach scale and the watershed scale. And with one of the authors here on this call, I want to be careful in saying that I handpicked some of these processes from the reach scale list and kind of use them to characterize, what are these valley bottoms? What processes are very important? And I'm not going to read through all these, but you can see there's just a very long list. There's a lot of processes that happen in these depositional environments because they are so complex. So I'll return to this list and kind of think about this list after we kind of talk about some of the disturbance. So the change condition, how have these depositional environments changed over time? And again, this is a Forest Service guy, so this is kind of my perspective on the change. Well, first you have to build a road up the valley bottom. And on Forest Service lands, that was followed closely behind by conifer harvest. Not only on the hill slopes, but you see some stumps down there right in the valley bottom, because that's where the big pumpkins were. And if they were logging these areas, they were also pulling out most of the wood out of these valley bottoms. And then we had a series of pretty large scale floods. 1964 was a big one in our area, created a lot of chaos because most of the stability in these riparian zones had been removed. And so it just created chaos with roads and campgrounds. And so we basically got out dozers and we started to put berms. We started to block and fill side channels and really try to control this landscape so that it did what we needed it to. And in a lot of areas throughout the West, conversion to grazing and farming, very common. And you could add mining and several other gravel mining we just talked about. The list is quite long, and Brian did a good job of kind of describing some of those log drives and the other things that have happened to our streams. But the upshot, and the previous speakers have talked about this really leads to, first of all, channel incision into the valley floor. Because you've gathered up all the water in this valley floor and you put it into one space, as Brian discussed in the stream evolution model, incision is usually what ensues. And along with that incision, you lose your water table. And really, the bottom line from an energy standpoint is that you change, as we mentioned in those first slides, you go from a depositional environment to a transport environment. And I kind of like to talk to these heavily incised stream channels as fire hose channels. And as such, most of the fine sediments are fire hose out of these systems, and you've got coarsened channel substrates. And this is important because a lot of people go to streams that are incised and they look at them and they look at the size of substrates at the bottom and they assume that those substrates were moved by that particular stream. And sometimes that isn't the case. Sometimes they were just uncovered by the washing that happened, and you see perhaps some glacial materials that were down below the valley bottom. And really a loss in that complex valley bottom habitat, a lot of the wood removed, as we mentioned, not much complexity. And there are folks that say, well, you know, we should just put a buffer on these streams and step back and just let them heal over time. And some healing does occur. We do get vegetation of some sort coming back in a lot of these incised channels. You, as Brian discussed, can get some channel evolution where banks will expand outward and you'll get a new floodplain at a lower base level elevation. But many things get stuck. And that's really what Brian talked about in terms of these stage 3S arrested degradation channels. And in our area of Oregon, where a bunch of us are working, we see a lot of these 3S channels. So your vegetation on the former valley bottom here turns to drier species because you've lost your water table. Because you've lost your water table, you don't have that storage or hyperheat cooling that you had. All this space in here is no longer storing water and slowly releasing. You only have a fraction of the rearing habitat that once existed in this real high energy channel. The food web greatly diminished because you just don't have those slow moving water areas, those wetlands, those complexes that are so important for the bottom of the food chain, the bacteria, the macroinvertebrates, the algae. And so you miss a lot of that part of the food web. And then juvenile species of all kinds are fleshed out, particularly in big storms. Colin Thorne likes to refer to these stage 3S channels as zombie rivers, and that's a really apt description because they're kind of dead and they don't know it. So I was going to pause here. A lot of what I just shared was very similar to what Brian shared, and so are there any questions in the chat or things that you want clarification on before I move to what were some of our traditional restoration? Gene, anything in the chat?
Nothing's come up in chat. And anyone, feel free to unmute your microphone if you have any questions or want Johan to elaborate here.
And I'll pause again in a little bit if folks want to ask a question. Give it some thought.
Okay.
Okay, so traditional restoration. So I came in as a hydrologist for the Forest Service in 1995, so mid-90s. So it had been about a decade and a half since restoration had kind of started in forest trying to restore many of these incised channels. And so I want to share just kind of some thoughts about what I saw and what I participated in throughout my career, just kind of see where we've been and how we've kind of moved towards stage 0 restoration in these depositional environments. So I would say early on, we had stream restoration goggles firmly ensconced on our head, and we had a very, very specific channel focus. Even in these broad, unconfined alluvial valleys, we were really focused on the channel. So we went out, we put our thermometers in the river, and we checked our stream temperatures, and they were very high. And we said, man, these areas need some riparian help. And so Forest Service does really well with trees. We had a lot of conifers in our tree lockers, Vexar tubes and conifers to get both the shade going and future wood. But it was a struggle. We had to really work at getting these trees to grow in these areas. Secondly, we knew that wood was a very important part of the system and that it had been removed in mass throughout national forest systems. We used to pull all the wood out as a requirement of logging that we did. We thought that that was limiting our fish passage, and so all the wood got pulled out. But eventually in the 80s, I think people started to figure it out. Folks like Jim Siddell, Hank Froelich, others started saying, you know what, we should stop pulling that wood out and perhaps put some back in. So we looked at these incised channels and said, man, it's going to be tough, but we need to get some wood and some boulders back into this system. And again, here's kind of a quick review of the types of techniques that we used. Thankfully, in the upper left, I was not around for gabions, but that was a doozy. We basically built wire baskets, filled them with rock, used rebar drilled into the bedrock, and we put these kind of cages on top and anything to just try and break up the energy of these bedrock dominated channels. By the time I arrived on the district that I worked on where they did these, it was just rebar sticking up out of the bedrock. Trying to get more natural, we moved to log sills at some point, quite natural, straight across, 20 feet apart, miles of this stuff. But again, we were trying to figure this out. We were trying to slow things down, collect some substrates. And so log sills was the thing for a while. Then we kind of moved towards a little more structure, some cabled structures. This is on the Coast Range in the upper right there. Lots of cable bolted into the bedrock, trying to get these short pieces of wood to stay in stream. Some of them did, some of them did not, but this was our attempt to try and get that form back into the stream channels and get them filled up and connected to our floodplains. Into the 90s, we got pretty sophisticated with engineered log jams, keyed into the banks, covering the banks, trying to create fish habitat with that at the same time. Massive structures like you see here in the bottom left. And then the last two procedures, we still use this quite a bit, truck-mounted yarders and helicopters to get wood, and sometimes wood with full root wads into our projects. Pretty important techniques that we still use. So when I look back at a lot of this traditional restoration, this channel-based restoration in these incised channels, I feel like we were doing our best. We were doing what we could to get things right, but we were pretty much stuck in the stage 3 and 4 and not really getting out of that. And if you think back to Brian's talk about in terms of productivity, ecosystem benefit, you really are at that lower side of the scale in terms of ecological benefit. You get those localized effects, you blow out some banks, you create some things. You might encourage some widening of some streams that may affect some floodplains, but by and large, when I look at a lot of the work that we did, it just didn't address the root problems. Back to Roney and Beachy's processes that are so important in the floodplain, most of those were happening in this area over here, and to a large extent, we weren't really connecting these areas and getting those processes going again. And I think it's really akin to kind of putting a Band-Aid on a zombie, is how I would put it. But I think our intentions were good. We were just kind of searching for how do we get these processes back. In the late 90s and early 2000s, many of us in the Forest Service went to Dr. Dave Rosgen's courses. He taught us a lot about bankful and how important that was. In these heavily channelized systems, he taught us to pond and plug. and then create a new meandering channel with the perfect plan and profile, or maybe not perfect, but an appropriate plan and profile, and the right bankful. He was very concerned about bankful, right? If you went to his courses, he told you, if you don't know bankful, you don't know shit. So that was what he taught us. And as we were starting to implement these types of single thread stable channel designs, he would show us how to use tow wood and J hooks and really try to deal with the energy of these stream channels all within channel. It wasn't about getting water on the floodplain. It was more having the proper bankful, having that stable plan and profile, and getting things done within channel. And so still that I would say that water table, we would partially bring that back up, but probably not to the historic levels. It did allow us to think more broadly about vegetation. I think we were still using a lot of upland type trees in these projects. And that was mostly because our water table was still not brought to the very top. And so just in general, I'd say we've got those stream restoration goggles on. We're really focused on the channel and what's happening in the channel, and not as much on the valley floor as a whole. And so what happened over time is we started to say, you know, we're reading these papers and we're seeing that the food is oftentimes on the valley floor in these pastures in these fields. They're doing studies and they're finding, where I was working on the Oregon coast, particularly coho, would be getting into these fields and just gorging themselves and creating huge size. So there was a real food aspect that we were starting to try and think about tying in. And so we actually started to undersize our channels that we were building and try to get water to flood. And then a funny thing happened in our undersized channels in a depositional environment, go figure, they started to silt in. And when those channels silted in, they would wet up whole portions of our project. And I would say after our initial shock and sorrow that we had lost our kind of engineered channel, we started to watch some of these areas that had filled in. We started noticing emergent veg coming up through this. Beaver were liking it, were coming in and starting to cut our willows and make dams. And we were seeing macroinvertebrates and juvenile fish starting to be attracted to some of these quote unquote failures in our engineered projects. And we started to really ask the question, instead of kind of falling into this, could we just create connected surfaces in these valley bottoms? And if we could do that, could we just connect entire valley bottoms? And then it happened. We took off our stream restoration goggles and we put on valley restoration goggles. This was the paradigm shift for us. I think we shifted away from thinking about channels and we started thinking about the entire valley bottom. We started looking at LiDAR. We started mapping relic channels that were completely dry in these valley bottoms. We started thinking about how we could, the best way we could reconnect these entire valleys from toe slope to toe slope. And how to do that at base flow, not just at some sort of flood flow, but how could we maximum connect everything we could. At about this time, when we were starting to put this together and implement these projects, the Kluwer and Doran paper came out in 2013. One of our practitioners, Kate Meyer, she sent this out to us and said, look, this is exactly what we've been talking about. And they gave it a name. It's called Stage0. Within about a year and a half, we had a field trip to look at projects on the Siuslaw, Willamette, and Deschutes and Ochoco National Forests. And so Brian Kluwer and Colin Thorne, also in these pictures, you see Michael Pollock. They came out and toured our projects and looked at the kind of work that we were doing. And they said, you know, we put together the theory, but we had no idea that there were crazy people like you that were actually putting some of these types of principles on the ground at scale. And so we've been working with these guys ever since, and it's been great. So the bottom line on restoration to Stage0, and again, we're talking about the far right of the diagram that Brian showed you at the end of his talk. This is valley bottom reset for severely degraded incised channels. This wouldn't be areas that would be very appropriate for PALs or BDAs to try and bring this back. So the long and short of what we're doing is we're removing levees and roadbeds, and at times even natural deposits. We're using that material to fill these deeply incised channels to a designed elevation based on LiDAR modeling that Paul is going to show you. And then we're putting abundant amounts of large woody material across this whole surface that we're working in. And one of the best byproducts of this whole thing, wait for it, watch the screen, instant water table recovery. Just uncanny. That water comes back up to the surface. We start seeing the emergent veg come through this stuff. We start seeing the sorting. We're essentially resetting this template and handing it back to the river. A couple points to make on this type of restoration. We're not constructing channels. There are times where we are bringing the water up to the point where it reconnects with relic channels that are in the lateral areas, but we're not actually out there constructing engineering channels like we used to. Another point I think I've already mentioned is the fact that we are looking for connection at base flow. So we're really looking for that anti-branching and kind of wetland dominated, very connected surface. We know that this surface is going to change over time, and we're allowing that dynamism to occur. The wood that we put in is buying us time because we know that at some point, when the vegetation recovers after the water table has been brought back up and the right vegetation recovers, we know that that's going to be kind of the dominant force controlling where channels go and what happens in terms of dynamism. So the wood buys us time to get there and also produces some very complex habitat. So I'm going to pause again before I show you a few examples. Just want to ask if we've got any questions in the chat or any discussion that we want to have kind of about that discussion before I show examples.
I see no questions coming up in the chat box. I have to say that's the best description of restoration evolution that I've ever seen. I really like that as far as where we've come and where we are. Okay, Rich just asked a question. Have you had any pushback from a water right perspective?
Yeah, maybe Paul Powers can address this one more because it happened on his forest, but we had one area that the Deschutes was working on called Ryan Ranch. And there was a lawsuit that came out asserting that we were stealing water from the irrigators. And that went to federal court, and I think the Forest Service won on that. We were not liable for stealing irrigators' water. But that's a very good question, particularly in arid regions, water rights are everything. And so I would say that they were most concerned about the timing of water release. We fill these valleys up like a bathtub. I don't know that we steal water from them, we just store it on the landscape longer. But it has gone to court and we did win on that one. Any other thoughts on that, Paul? Do you remember how that went?
Yeah, you got that summary right there, Johan. That's it.
And I'll just add on that topic. Yes, that is a concern that comes up, and it's yet to be fully litigated. I think it's an issue right now in Colorado, but California, for example, which has just as many water problems as any Western state, has encouraged the restoration of mountain meadows with the main goal of storing water higher in the watershed for improving water supply downstream. So I think the science is pretty solid that these projects don't steal water, quote, steal water, but they do have to fill up. And I think you'll see some, I know I'll show you one example, and I think Johan will show you another example coming up where they fill up really quickly. And after that, then it's equilibrium on water supply.
And how have you dealt with heritage issues in these areas with historical and cultural activities?
Yeah, super important on Forest Service lands. So we do have archaeologists on our interdisciplinary teams. They review all these sites. They are very familiar with what exactly will happen. And we have to adjust our design if there is something we do not want to disturb. So very good point. At least on the Forest Service lands, we have interdisciplinary teams, and all the resources need to be looked at. And these are one of them. And oftentimes these valley bottoms are laden with archaeological artifacts and things that we really need to be concerned about. So I can't think of any of our projects that were waylaid or completely altered by an Archae site yet. Maybe others on can tell me differently, but yes, very much concerned.
And maybe as you get through these examples too, it would be helpful to talk about landowner. I'm sure you're probably going to get there too, but that's if it's mostly Forest Service land that's owned, that gives perspective on the water rights and the cultural. So a question commonly comes up on how do you maintain fish passage with Stage 0 projects? And that came into the chat as well. So that's something to think about either now or throughout your examples as well. But I know that's a common question, is how is fish passage maintained? Do you want to speak to that right now?
Yeah, I'm going to leave some of that for Kate Meyer, who is a fish bio. What I will say is yes, in Oregon, particularly our state agencies, Oregon Department of Fish and Wildlife is very concerned about fish passage in general, and I think Kate might show you some of this. We're finding that we have deeper flows, we have deeper pools after we get done. It seems counterintuitive because people say, well, how can that be? Because you're spreading water much wider. It should be, 2 inches thick all the way. What you're doing is creating a very roughened surface that slows water way down. You're essentially piling up water. We also leave low spots. We don't fill everything. So we've got portions of our incised channel, small portions that we leave unfilled, and they become very deep pools. So we try to address all types of habitat while we're doing this. But yes, there are concerns. I don't think that we feel like they are legitimate concerns because we're showing from our data that the water is actually deeper when we finish. Kate, you can touch on that too, if you would, in your talk.
The question came up, are there any of these projects in regulated rivers, for example, below a dam or diversion?
Yes, funny you should ask. Kate is going to share something from the South Fork of the McKenzie, and that's directly below a dam, a 4-mile stretch right below a dam. So yeah, some very interesting considerations for that.
Okay, great. And then as a follow-up to the question on water rights, has anyone been able to quantify how water delivery has changed downstream of a project reach following restoration?
Not to my knowledge, not yet, but I think eventually we'll get there. Brian, do you know of any of that?
Yeah, there's some literature from a couple of California mountain meadow restoration projects on increased water supply. I can't think of the authors off the top of my head, but it's been studied and it was found to be positive.
Thanks, Brian.
Okay, we'll put the questions aside now. Nothing's popped up, but we've got about 15 minutes before our lunch break. So go ahead, Johan.
Great. Okay, so you see in front of you here, these are the Oregon ecoregions, and you see a number of projects here. I don't think I have all of the ones that we've done, but we've done something like 25 different Stage 0 projects, and they vary in size, scale, and ecoregion throughout the state. And so I've kind of handpicked 5 of those, one from each of 5 ecoregions throughout Oregon. I've got kind of the statistics on each one, so you can kind of see the wide variability of the places that we're working. So I'm going to start on Lost Creek in the Northern Basin and Range, go to Deep Creek in the Middle Rockies and Blue Mountains. Over on the east slope of the Cascades, I've got Whitechoose Creek, Deer Creek, which is also one that Kate's going to talk about. So I'm just going to talk about our first phase of that and kind of some of the things that we did the very first time around. And she'll talk more about the learning lessons that we received from that project. And then over out on the coast, a very flat coastal plain example, 5 Mile Bell, with Paul Burns and the Sayus Law. So this is Lost Creek. This is a Nature Conservancy property. And you can see the inset photos there of kind of what the degraded condition looks like. And I really love this, this example because it illustrates what head cuts do. So flow, as it shows here, is going from bottom to top. There is a geomorphic constraint right here. You can see the outcrops and the bedrock. And then it goes into a transport channel, kind of an incised canyon through here. But this is a depositional environment that formed above this nick point here at the bottom. And what you can see is that this channel head cuts all the way up. It's cut down into the valley floor, like we talked about, and it makes its way up and it stops right here. And the reason I know, besides seeing a gaping open wound, the reason I know that the head cut stops here is that you can see the difference in vegetation. See how it's darker color here in this upper portion? That hasn't incised, that hasn't drained. So it's just such a great example looking from the air of something that's been thoroughly drained by a head cut and something that hasn't yet been drained. So it's like the bottom end here, the plug's been pulled out of the bathtub and it's been drained. And thus, this is kind of what this incision looks like in these pictures here. You can see the water coming down at the top of the head cut. So a few statistics for Lost Creek. We mentioned Northern Basin and Range, Nature Conservancy. We're at 4,000 feet elevation here, less than 10 inches of rain per year, dominant disturbances, grazing, levying, beaver extirpation. And of course, this was all before Nature Conservancy purchased the property as a conservation property. It's a very small project area, only 8 acres. Your valley substrates are really fine grained soils, and your valley slope is about 3%. And your average valley width is something like 300 feet, 90 meters. And your native fish are red band trout. So if you look at this map here on the left of the screen, you see the general idea of this restoration. We've got these hatched polygons here, kind of various depths of material that's going to be scraped from these, and we're going to use that material to fill these incised channels all the way down to this nick point here at the bottom. Okay, so that's our goal. They essentially built some sort of a channel around this to divert water. They rescued any critters out of that incised channel before they filled it. But the next pictures you will see are of them doing the work. Upper left here, you see the machines working in the source areas. They're trucking the fill material down and filling these portions of the head cut channel, about 8,000 cubic yards total, working it in with an excavator in the top right. And here's kind of the finished messy product. Okay, and then look at this spot right here. This is a couple years later, and you can see by the color of the vegetation, you've got water that's being maintained in this valley, unlike what we saw in that first picture. And one of my favorite before afters here, the ugly head cut here, after it's been filled, this is about 3 years later. You can see the water at the surface. You see the emergent veg coming up through here. So Rob Tanner is standing next to about in the same spot. And if you take a look at the picture at the bottom, you can kind of see, get a taste of the high water table and the wetland veg that you see there. So that's Lost Creek. Moving to Deep Creek on the Ochoco National Forest. This is a recent project that Paul Powers designed and implemented. It is in the Middle Rockies, Blue Mountains ecoregion. This is Forest Service ground. We're at an elevation of about 4,300. Average precip, a little wetter, about 12.6 inches per year. Dominant disturbances, pretty typical of the Ochoco National Forest, lots of grazing and some channelization and levying at this point. About 35 acres this project is. Valley substrates, fines, and gravels. about 1% valley slope, and the average valley width is about 310 feet. And at the bottom, I have a funny frame around my slides here. I don't know if you guys can see the bottom of my slides, but the native fish here are red band trout. So Paul's going to talk a little more about the modeling that he does using LiDAR, but this is what we call a relative elevation map. This is a detrended map that essentially color codes elevation based on what we call a geomorphic grade line. The geomorphic grade line is essentially the valley fall, okay, the valley slope, not the channel slope, but the valley slope. And so when we detrend that LiDAR image, basically we can pop out and look at by color, where are the old relic channels, where is their incision, where do we have possible source material. This really helps us plan and design our project. So for instance, as you look at this map, you can see the channel here with kind of a dark pink color. That means it's incised. In this case, it's about 16 decimeters, which is about 1.5 meters. So 1.5 meters incision when compared to the light blue, which is our geomorphic grade line, kind of our target historic elevation. So the pink is below that light blue, which is our 0. Above that, the greens, yellows, oranges, reds, those are all above. One quick note here, and I think Paul would describe this better than I, but this is a problem that we often have when we deal with a project, a lower end of a stream channel that's rejoining a larger channel below. This is the North Fork Crooked River. It's also heavily incised, heavily just incision into the valley floor. And so if we were to bring this up to a more historic elevation, we have to transition that back down into this incised main stem. Okay, so elevation and doing those transitions right are very important to our work. And so what Paul explains here in the left bar is that this black line begins the transition from historic elevation, transition back down into something that's lower because it's incised. And essentially what Paul did is designed an alluvial fan, kind of a steeper alluvial fan, to come back down into the North Fork Crooked River. Paul, did I hit that right?
Perfectly.
All right, let's show some pictures of it. So that's me on the far right, looking down into the chasm with Mark Lehner. Keep an eye on that yellow circle there, because it's going to get drastic here. Next picture. So this is mid-project. We've diverted the water, the flow, obviously, into a diversion channel. We've entirely filled that ditch that was there before, and we are at the designed geomorphic grade line elevation for this portion of the valley. Couple more pictures just showing it's pretty raw. We have a little bit of wood that we can put on top of this and some veg, but we've essentially filled all these areas up to our target elevation. So here, if you look at this map on the left, we're down at the confluence with the North Fork Crooked, and there's an old road bed that comes across right where this comes into the North Fork. And this is what it is. It's kind of probably a waste area that they turned into a road, but it's essentially a levee at this point in time. So as part of Paul's design, he had to remove a bunch of that material to essentially implement his transition idea and his alluvial fan idea. So here they're excavating material, and they're likely using this material upstream in those heavily incised portions of the channel, using it to bring it up to desired elevation. And then this is kind of right after he's gotten his elevations right, and he's put a bunch of slash and wood on it, and he's introduced water back on.
Johan, if I could interrupt, just one of the questions is, how do you manage turbidity when we pre-watering? And then also there was another question on how long does it take for fish to be able to utilize the new habitat once the restoration is complete?
Yep, I'm going to defer the fish use to the fish bios, but the short answer is almost immediately. turbidity is a big planning thing for us. So we do whatever we can to put silt curtains up. We use diversion channels that will cause some turbidity for short periods of time, but then clear up again. We do a lot of thinking about turbidity because our permitting agencies in Oregon are very concerned about that. But yes, we do break a few eggs and we do have flushes of turbidity, and we're very honest about that in our NEPA, our environmental documentation. But what we see is that these things clear up very quickly, amazingly quickly. But I am going to defer some of the fish questions to Kate and Paul in their presentations. But turbidity is a big one for us, and we've learned a great deal about how to do that more efficiently. But when we're at this stage that you're looking at here, there's not a whole lot you can do. You're going to wet it up. You are going to create some turbidity. We have to inform the public at times. This Deep Creek project is a little farther out in the hinterland, so there's probably not going to be as many calls, but a lot of the work that we do on the west side has a lot of public component, and we have to inform people that we're going to do it. So moving on, we see sedges colonizing very quickly in the areas that we fill. That seed bank remains in some places. We have to augment it in others. You see a bunch of rushes here in the flooded areas, immediately taken off. And I'm literally seriously saying in about weeks, we start to see this vegetation pop through and start going nuts. They love water table. I mentioned earlier, we don't fill all portions of the old channel and areas, and we leave some as ponds. We get lots of wood in that, and so these are some of the deeper areas. You see a lot of fish use in these. That's an important part of our projects as well. Just the next few pictures showing after the valley has completely watered up. You can see water in several areas of the valley bottom in this picture. These are all, this is relic vegetation islands that we left behind, and they're going to be thriving, most of the species in here. Lots of pictures of emergent veg, very happy. Okay, and finally, this is the final picture for Deep Creek here. This is that confluence fan that Paul built, and within a year we had beaver building dams on this. Pretty amazing, pretty awesome. And you see the kind of 400-foot wide confluence area, just a lot of water, looking really good. Anything to add, Paul?
No, you did great. That's 1 month later. So it greens up fast, and the beavers found it too.
Okay, I'm going to move through these last projects a little quicker because I see that I'm really almost out of time here, and I want to get you guys to lunch. This is Waichu's floodplain. This is East Cascades, high desert. This is kind of an outwash plain. Waichu's comes out of the mountains and spills across. Over time, logging and channelization really altered this, and so you're going to see a lot of kind of ditchy looking stuff. And these guys came in to this 120-acre area and really reconnected filled up these ditch channels and reconnected a bunch of this floodplain, and it's really quite awesome. 1% gravel cobble fines, but about a 2,000 feet wide outwash plain is what they worked in. So at the top there, you kind of see the series of ditches. And the bottom, you see it reconnected. Paul often states that you see about a third of the channels in this picture at the bottom. The other 2/3 are within the forest there to the right.
And what's the timing of that 2015 after picture? Is that a 1 year after, multiple years? I missed the year of the construction.
Paul, can you answer that?
He said 1 year on the chat box. Thanks, Paul.
Okay, so just some close-up shots, just a lot. You can see some fines starting to settle out in the foreground of this. You see the emergent veg coming up. You definitely see some conifer trees that are flooded here and will probably succumb. We totally understand that because, as I mentioned earlier in the disturbance pictures, when these areas were dewatered, a lot of drier species and conifers came into these areas. they will die and they will add to the wood component of this project. See the kind of bacterial level starting to really work in those orange areas, kind of iron deposits. That's the base of the food chain, really starting to kick again. Some before afters, big piles of substrates on the upper left, and then kind of the regrading of that whole thing. This is immediately post-project. And then 2 years later, you can kind of see by the color of green, you've got water table in all these lateral areas. And Paul tells me this, when they do their fish surveys, this is just packed with juveniles. Okay, on to Deer Creek. I'm on the west side, and I'll kind of go through this quickly because Kate is also going to share this project and kind of what we learned. This is the lower 1.5 miles. You can see in that right photo, there's a lot of confined channels that feed into this lower 1.5 miles of Deer Creek, and historically, this was a very rich place. However, if you could maximally disturb a stream, this would be the place where they did it. Logging, followed by the 1964 flood, channelization and leveeing with heavy equipment, building of berms, power line construction up the middle, road construction, not a pretty place. So essentially this is after the 64 flood, destabilized by logging. They went through with cats and they cut off all the side channels that you see in this picture. They removed all the wood, either burned it or sent it to the mill. And essentially what happened over the next 60 years was pretty desperate habitat conditions. So the upper left is a big old berm left over. You see the boulder ditch there in the middle, and then high flows are just a torrent. The floodplains on either side of that right picture are completely disconnected. They're now terraces. There's all sorts of relic channels in them, but they just aren't connected at all. So very, very degraded condition with not a whole lot of potential for restoration. Unless we think about taking those berms and artificial features, regrading those to fill the incised portion, definitely a reset in this gray swath. Add the large wood, and then we also pulled a number of trees in, whole big trees, to just create more complexity. Then we allowed flow to just go through this and form its own paths, no constructed channels. Relic channels that were reconnected, but no constructed channels. So just a few pictures of the implementation. We do have some big trees on the west side, and so we were able to work with wildlife to create some early sterile gaps in the same sub-watershed. We got 200 trees between 24 and 36 inches. Big machines pushed them over, snapped them in half, and hauled them down to our project site. Here we are reworking the valley bottom materials, filling those incised portions of channel with dozer and excavator. And then installing those 450 pieces of wood in a series of jams throughout the 35 acres that we worked in. And again, Kate will talk a little bit about what we learned in terms of this wood and placement and how we would do it differently. We learned a lot. This was our very first Stage0. And then finally, truck-mounted yarder used to pull whole large trees, 25 of them. Look at the size there, 38 to 63 inch diameter pulled over. Again, that is a luxury of the west side. We have some big trees. So bottom line here at Deer Creek, and I think I'll end at this slide because I believe I'm out of time and then some, get you guys to lunch. But the untreated reach at the top there, kind of a boulder ditch, 10 meters wide. When we've treated it, you can see about 4 times the connection. You're also seeing, instead of boulders in the picture, you're seeing cobble, gravel, fines, lots of wood. If you look at those pie graphs on the right, the untreated, 2/3 of that habitat is riffle, just straight shot riffle. And after the treatment, right after the treatment, we've got more like about 3/4 of it is pool or glide, much slower moving water through this reach. And Gene, I've got another project, but I think I'm going to end there because we're out of time.
I'm sorry to hear that, but I appreciate that. We should keep the schedule. It's all pretty fascinating. We did have some questions arise in the chat box, but maybe we can talk about that a little bit more after lunch. And just to mention to the other speakers too, if you see questions as someone's giving a presentation, feel free to answer them as well if they're coming up, because we don't want to get too far behind on some of these questions. But that's a great presentation, and I guess it's 12:15, so I probably shouldn't even take any questions, but we will not be turning the go-to off. So whatever's easiest for the audience, if they want to keep in the meeting while we go to lunch, we'll have it continued here, so you won't have to re-log in. Or if you want to re-log in, that's fine too. After lunch, we will maybe we'll start with some question and answer. I'll talk to Kate about how we want to start that after lunch. But Kate is going to be our next speaker, and we will plan to be back here right at about 1:05. I'll be back in at 1 to make sure everything's working, and then we'll get started with the next speaker right at 1:05. Does that sound okay to everyone? Since I've got you all muted, I'm going to say that's a yes. And we'll have a great lunch break. We'll be back here at about 50 minutes. Thank you, everyone.
This conference will now be recorded.
You can see there to the
Sorry,
far.
Johan.
No problem. No
I
problem.
forgot to turn the recording on. Someone reminded me. I'm so sorry for that. Go ahead.
No problem. That's punishment for not finishing before lunch, so that's good. But anyway, so on the far right there, you see that by 2018, 4 years after project implementation, they really have a solid hold on native vegetation, which can be a very tough thing in the Coast Range. So that's the 5 Mile Bell project that I wanted to share with you guys. So in summary, just wanted to kind of reiterate the main points. Widespread distribution of successful Stage 0 projects is really what I wanted to portray. Really restricted to those depositional or response reaches. That's where we're focusing on these things. The scale matters is what George Pest told us, and I agree. So if we're going to invest our limited dollars in places, it should be these depositional areas because they are the producers. They were historically. As asked earlier, people said, what gradients does this work on? I've shown you about 0.1. The last project was 0.1, very low gradient, up to about 3%, but we've done one as high as 6%. Paul Powers can tell you about that. Anything when you look on a LiDAR image, bare earth LiDAR image, and you can see a floodplain next to a stream channel, you have potential to do some Stage 0. Low to high precipitation areas, the principles are the same at all elevations. Multi-phased adaptive projects can be accomplished. I think Kate's going to show you a couple of those next. And just remember that not all reaches of a stream function the same. And again, I think Paul Powers will show you that in his example that he's going to show you a relative elevation map for. And 2 to 5 year return interval flooding is not the same as Stage 0. We try to connect these things so that at base flow, they are connected. So to some degree connected year round. That's all I got. Thanks for letting me finish.
Of course, that was great. Thank you. Do we have any questions here before we move to Kate?